Okay, we're going to do a recording of the solutions for Chapter 1 review. Okay, on this first problem here, it says write the equation line through this point with this slope. This is just back to Algebra 1. Instead of using the point slope formula, which is y minus the y coordinate equals the slope times x minus the x coordinate, we're just going to put the y coordinate on the right side right away. So y equals the y coordinate, which is 2, plus the slope, which is negative 1/3, times x minus the x coordinate. Now x minus negative 1 becomes plus a positive 1. This would be called a linearization form. Sometimes I'm going to ask you to leave it in that form right there. Okay? However, this one asks for slope-intercept. There's just two mathematical operations, actually three, that you have to do to convert. Distribute the negative 1/3, which is negative 1/3 x. But here, negative 1/3 times 1 is negative 1/3 plus 6/3. 6/3 minus 1/3 is a positive 5/3. If you need to write more of those fractions down, you certainly can. I'd like to see you practice distribution, common denominator, adding all in one step. Okay? 2 is going to be the exact same problem, except for they do not tell us the slope. We have to determine the slope ourselves. And we can do that by just subtracting the y's over subtracting the x's. So the slope is going to equal. Remember, it's change in y over change in x. It doesn't matter which point we start with as long as we're consistent. So I'll start with this point. 1 minus negative 4. Subtract the y coordinates of the 2 points on top. 2 minus negative 3. Okay, the slope formula, subtract the y's over subtract the x's, is also called the difference quotient. And this problem for sure is going to actually be on the AP test. Just subtracting y's over subtracting x's. So right away with the second problem, we're already running into a problem that's going to be on the AP calculus test. So the slope is 1. You can use either this point or this point. So there are two potential solutions. But I ask you to leave it in linearization form. We do not need to convert it to slope-intercept. So y is going to equal the y coordinate, negative 4, plus the slope, which is just 1, so we really don't even have to write that down, x minus the x coordinate. X minus negative 3 becomes x plus 3. That's one way that you could write the answer. The other one would be the y coordinate, which is 1, plus x minus the x coordinate. Either one of these would be correct. You do not need to list both, just one. I'm writing both down so that you can correct your assignment. Notice with either one of these, if I converted to slope-intercept, I would get x minus 1. Here I would get x minus 1. They both convert to the same slope-intercept. Why do we leave them like this? On the free response, this is how the equations of lines are going to be written almost every time on the free response. Okay? Why do we convert to slope-intercept? Because most multiple choice questions will be converted to slope-intercept. And it's just a couple mathematical operations to do that. Find the equation of the vertical and horizontal line. It's this easy. A vertical line through a point is always x equals the x coordinate. A horizontal line through a point is always y equals the y coordinate. Done. I'll have blanks just like that for you to write it in. 4. Find an equation for line through the given point parallel to the given line. Well, we have to first find out what's the slope of this line. So I'm going to subtract the 3x to the other side and divide each term by 2 to eliminate the 2 times y. That is the equation of the original line that was provided. Now, they want us to find the line that is parallel. So you have to read carefully. This one says parallel. I could just as easily ask for perpendicular. Okay? Well, let's do parallel. Remember, if a line is parallel to another line, it has the same slope. So I have this slope right here. and it's going through the point 32. So we do the exact same thing we did in problems 1 and 2. Y equals the y coordinate, which is a 2, plus the slope, which is a -3/2, times x minus the x coordinate. That is linearization form right there. If it said linearization, we would leave it. But it says convert it to slope intercept. So we are going to have a -3/2 x. So I can write that down right away. Now I just have to be careful. Negative times negative is positive. The 2's cancel, so it's a +3 plus a +2 is a +5. Except, let me say that again, x minus the x coordinate. So let's do that again. I put x minus the y coordinate. X minus the x coordinate. Now I'm going to get +9/2 plus 4/2 is a +13/2. That's better. Okay. There it is. Problem number 5. Find the equational line through the given point and perpendicular. So the exact same problem as 4, except now this says perpendicular. And we need to know that the slope of perpendicular lines are opposite reciprocals. So the slope of the perpendicular line is the reciprocal of 1/2, which is 2, but I have to negate it. We're leaving this one in linearization form. Y equals the y coordinate plus the slope plus -2, so I might as well just write subtract 2, same as saying plus a negative, times x minus the x coordinate. X minus -1 becomes x plus 1. Okay? There it is. Page 1 is all Algebra 1. It will be similar on your take-home test for sure, and probably pretty similar on the absolute or on the actual test. Okay? Take a look at problem number 6. We're going to sketch a complete graph given the give the domain and range in both set builder and interval notation. Write a piecewise function. List the x and the y intercepts. Provide at least 5 quality points. We can start by just providing quality points here. Plug in values for x. I can plug 2 in. 2 minus 2 is 0. 2 times 0 is 0, and 0 plus 1 is 1. If we plug 3 in, we end up getting 2 plus 1 is 3 back out. If we plug 4 in right here, absolute value of 2 is 2, times 2 is 4, plus 1 is 5. But we need to go to the other side of this most interesting value of x. So if I plug 1 in, 1 minus 2 is -1. The absolute value of -1 is +1, times 2 is 2, plus 1 is 3. What about going to the left another value? 0 minus 2 is -2. The absolute value of -2 is +2. 2 times 2 is 4, plus 1 is 5. Here it is. To the right 2 up 1. To the right 3 up 3. To the right 4 up 5. To the right 1 up 3. 0, 5. And we can see that this is this V-shaped curve. Okay, V-shaped function. And if we just connect the dots here, if you have a straight edge, great. But here it is. We could count it out the slope. Okay, actually I should count out better than that. Here it is. So make sure you have a good quality graph. There it is. Let's start then with the piecewise notation. Remember, this function is going to act completely different to the left of 2, as we can see from the graph, than it does from the right of 2. So I'm looking at 2 intervals, when x is less than 2 versus when x is greater than or equal to 2. I will say again, the equal to can go here or here, but not both. I typically put it with the positive portion of the graph, because when we take the absolute value of 0, we don't change the sign of 0, it's just 0. So I typically put it here, but it would not be wrong. It was in either spot. But what I do know is any number that's less than 2, when I plug in 1 or 0 or -1, I get a negative number inside the absolute value notation. So in order to make a negative number become positive, I have to negate it. So for any value of x that's less than 2, I need to negate this right here. The 2 is still out in front, but if I negate this, it's negative x plus 2. And then don't forget to add the 1. And if I distribute the 2, I get negative 2x plus 4 plus 1, which is negative 2x plus 5. That is the left-hand piece of this piecewise function. The left-hand piece would go first. Negative 2x plus 5, comma, and then the domain. It must be written in proper piecewise function. Describing the graph from left to right, goes top to bottom, functional part first, then the domain. Has to be correct. Okay, when x is greater than or equal to 2, these absolute value bars are meaningless. The number is already positive. So it's 2 times x minus 2 plus 1, which is 2x minus 4 plus 1, or 2x minus 3. 2x minus 3, comma, then the domain restriction. X is greater than or equal to 2. Do not have the equal to in both spots, only in one. So far, so good, hopefully. X-intercept, remember we can always find the x-intercept by plugging 0 in for y, but look at my graph. I can see the x-intercept is none. The y-intercept can always be found by plugging 0 in for x, 0, comma, 5. By the way, if I would have plugged in 0 for y right here, subtract 1, divide by 2, the absolute value cannot produce a negative number. So we can see why we do not have an x-intercept algebraically as well. The domain, I'm not taking the even root. I'm not taking an even root. I'm not dividing by 0. And I'm not doing a logarithm. So the domain for this is all real numbers. We can plug anything in for x, element of all real numbers. Remember, on this test, you have to do both set builder and interval. Okay? There is a range restriction. The smallest value of y is 1. So y is the element of all real numbers such that y is greater than or equal to 1. So bracket 1, comma, positive infinity. So sometimes I'll put a plus in front of it, but if it's positive infinity, you really don't need to. Oops, I'll move it up there so you can see it. You really don't need to, okay? That is the range restriction on that one. Okay, moving on to problem number 7. We're going to do a complete graph again, give the domain and range in both set builder notation and interval notation, list x and y intercepts as coordinate points if they exist, and provide 4 quality points. You can point plot right away if you want to. Maybe that will help you discover this fact. If I plug 2 in, because that's the most interesting value of x, 2 minus 2 is 0. The square root of 0 is 0. 0 plus negative 4 is negative 4. Can I plug 3 in? That works out well. 3 minus 2 is 1. Square root of 1 is 1. Negative 4 plus 1 is negative 3. Could I plug 4 in? Yeah, but I'm going to get an irrational number. 5 is going to give me irrational. 6 works well. 6 minus 2 is 4. The square root of 4 is 2. Negative 4 plus 2 is negative 2. And I don't want to plug in 7 or 8 or 9. They all produce irrational numbers. Okay, even 10. The next one that you could plug in is actually 11. 11 minus 2 is 9. Square root of 9 is 3. Negative 4 plus 3 is negative 1. Now this one doesn't fit on the graph, but you should be able, whatever I give you here, you should be able to fit on a good graph that I'm going to provide for you on the actual test. So if we go to the right 2, down 1, 2, 3, 4. If I go to the right 3, I'm going down 3. If I go to the right 6, I'm going down 2. And if I go over 11, I'm going down 1. Okay? So I want to keep that in mind. And if you know that even roots are half, right? At least a square root is half of a sideways parabola, right? A parabola that lies on its side. That's all it is. Why is it only half? Because we have a domain restriction. We cannot take the square root of negative numbers. So when I'm determining the domain, do you have to write this down? No, but I'm just showing this systematic approach is to always set the argument greater than or equal to 0. We can take the square root of 0. Add 2 to the other side. There's our domain. Okay? We can see from this picture the range then is going to be y values are larger than negative 4. That is the smallest y value, and then it grows from there. So let's start with the domain and range. Domain. X is the element of all real numbers. Oops. X is the element of all real numbers such that x is greater than or equal to 2. Remember, in set builder notation, that's bracket 2 to positive infinity. For the range, and we do have to have a picture of the graph in order to determine this range. And remember, it's the only intervals given in terms of the y coordinate. So y is the element of all real numbers such that y is greater than or equal to negative 4, because that is the smallest y value that we have on our graph. That means in interval notation, it's negative 4 to positive infinity. Okay? Finding x and y intercept, same thing every time. To find an x-intercept, plug in 0 for y. To find a y-intercept, plug in 0 for x. This one's actually the easiest if it exists. If we plug in 0 for x right here, I can't do that. It's not in the domain. I can't take the square root of negative 2 and get a real number. So this is none. And we can see from the graph that it doesn't cross the y-axis. It is going to cross the x-axis at some point. So if I set this function equal to 0, that's plugging in 0 for y. I can solve this. I can add 4 to the other side, square both sides, and add 2 to both sides of the equation to figure out that the x-intercept is actually 18. Even though it doesn't fit, I want you to list that x-intercept on this problem. Okay? So there it is. I'll leave it there just for a second in case you need to get any of those solutions down. It's problem number 7. The next two graphs are often create some problems for students. Let's read it carefully. Sketch a graph complete graph. Give the domain and range in both set builder notation intervals, same direction. List x and y as coordinate points, same before. List at least 4 quality points in the t-chart, so we know we have to do that. At least one point must have a fractional output. So we are inputting for x here, and at least one has to be a fraction. We don't want to input fractions, we want to get out a fraction so that we can see how it approaches the asymptote. Okay? List any asymptotes. Label the asymptotes as a vertical or horizontal. On these, I do think it might be better if you start with the domain. Okay? Start with the domain and start with what you know should be the horizontal asymptote. So I'm going to come down here quickly. This is an exponential function. We can plug any value in for x. I'm not taking the even root of a negative number. I'm not dividing by 0. And nor will I have a situation in which I'm taking the logarithm of 0 or a negative number. So my 3 major constraints for domain are not in consideration here. So again, the domain is all real numbers. This is the way I want it written, set builder notation. Remember, do not use ARN for all real numbers. Okay? The range we will wait till we graph, but if you can identify the horizontal asymptote right away, it's going to help with this. We have a horizontal asymptote for exponential functions. Because as this number gets large in the negative direction, this value is going to get closer and closer to 0. And 0 minus 1 is going to be negative 1. This number that's on an island by itself, that is a term by itself, y equals that number is always going to be the horizontal asymptote. Now, I have 2 blanks on the asymptote because I want you to identify the fact that this is a horizontal asymptote, not a vertical asymptote. And a horizontal line is always y equals the number. Y equals negative 1. And you have to make sure that you have the y equals. If it just says negative 1, that will be marked incorrect. It has to be y equals negative 1. Okay? So we can dot in this asymptote at y equals negative 1. And I'll do that right away. So that if I dot it in right away, I know that my graph is going to approach this asymptote. I just don't know if it's going to come this way or this way or this way or this way. I'm not sure. So let's start plotting some points and see how this graph evolves. But if you can determine the domain and the horizontal asymptote, that's going to help. Most interesting value of x is negative 2, because negative 2 plus 2 is 0, and 2 to the 0 is 1, and 1 minus 1 produces a 0. I'm just going to keep working to the right of negative 2, negative 1. Negative 1 plus 2 is positive 1. 2 to the first is 2, minus 1 is 1. 0. 0 plus 2 is 2. 2 squared is 4. 4 minus 1 is 3. How about it? We can keep going here. If I plug in 1, I'm going to get 2 to the third power is 8. 8 minus 1 is 7. That gives us 4 really good points in that direction. But we always have to go to the left of this most interesting value as well to see how the curve is approaching the asymptote. If I plug in negative 3, negative 3 plus 2 is negative 1. 2 to the negative first power is 1 over 2 to the first power. It's 1/2. Minus 1 is negative 1/2. Now, you're not going to have your calculator on this test, and you have to be able to evaluate these negative exponent situations. I'm going to do one more just for good measure. Negative 4 plus 2 is negative 2. That's 1 over 2 squared. In order to make an exponent positive, I drop the base to the denominator and change the sign of the exponent. 1 over 2 squared is 1/4. 1/4 minus 1 is negative 3/4. I could plug in negative 5 and get out negative 7/8, and negative 6 and get out negative 15/16. It's going to get closer and closer and closer to y equaling negative 1. That's why our horizontal asymptote is y equals negative 1. But we're discovering it as we go. Let's plot these points. Back 2, up or down 0. Back 1, up 1. Left or right 0, up 3. To the right 1, up 7. Now if I go back 3, I'm going down 1/2. If I go back 4, I'm going down 3/4. If I went back 5, down 7/8, down 15. It's getting closer and closer and closer to y equaling negative 1. There it is. And now we can see from this picture that the y values are always above this horizontal asymptote. So the range. Y is the element of all real numbers such that the y values are greater than negative 1. That is negative 1 comma infinity. X-intercept. Well, it definitely crosses the x-axis. So we'll talk about that here in a minute. Y-intercept is always the easiest because I just plug in 0 for x. Well, I already did that right here. That's the point 0, 3. Can we solve for this x-intercept? Yeah, just plug in 0 for y. Plug in 0 right here. We can solve this. You can see it right here that you already found the x-intercept, but if you were to plug in 0, add 1 to the other side, take the natural log of both sides. You could solve it as well to get -2, 0. Okay? And we actually came upon it as we were graphing this. So we'll just fill it in. Okay, so for problem number 9, logarithmic functions. And again, keeping straight 8, 9. I got them back to back so that hopefully we can keep them straight. Remembering that logarithmic functions are inverse functions of exponential functions. So if exponential functions have horizontal asymptotes, then logarithmic functions typically have vertical asymptotes. And the vertical asymptote is going to occur wherever this argument equals 0. So I'm going to do this one like I would normally do it. So the first thing I want to do is identify my vertical asymptote, and I'm going to write that in right here. I'm going to identify that it's a vertical asymptote. And remember, vertical lines are x equals the number. X equals 1, because 1 makes this argument equal 0. And while I'm on the same topic here, I'll dot in my vertical asymptote. Do it nice green this time. So I can see it real clearly. While I'm on this vertical asymptote, I might as well talk about the domain, right? Because the domain of a logarithmic function will have a domain restriction if this argument ever is 0 or a negative number. Well, how do I check that? Well, I just simply set the argument greater than 0. It cannot equal 0 because it can't hit this vertical asymptote. You cannot take the logarithm of 0. Add the 1 to both sides, there's the domain. So that would be the next thing I would find. X is the element of all real numbers such that x is greater than 1. That is parentheses 1, comma, infinity in interval notation. The range will do after the picture, but remembering that typically the range is going to be whatever the domain was of an exponential. Domain of most exponentials is all real numbers. This is probably going to be all real numbers. But I'm going to ask you to rewrite this in exponential form, and this is where some students will struggle. To rewrite this in exponential form, I'm going to show the work right here. Y equals log base 3 of x minus 1 plus 2. I want to solve for x in terms of y when I do this. In order to do that, at some point I need to undo this log base 3. Well, 3 raised to undoes a log base 3, but I cannot take 3 raised to both sides until I have a log and an argument only. So I have to subtract the 2 to the other side first. Now I can undo this logarithm because it's a log and an argument only. So now I can take 3 raised to both sides, 3 raised to the y minus 2. And if I take 3 raised to the log base 3, those two functions are inverse functions. They cancel each other out. And if I add the 1 to the other side to isolate the x, I'm going to get x equals 3 raised to the y minus 2, and then I'm subtracting 1. Now, why would I do this? Because now it makes this point plotting easy. I just have to realize for logarithmic functions, my y value is going to be my input. The x is going to be the output. So notice I say at least one point must contain a fractional output, not an input, an output. So I'm going to input integer values with the most interesting value of y being 2. 2 minus 2 is 0, 3 to the 0 is 1, 1 minus 1 is 0. I'm just doing the exact same thing I did last problem, except now I'm inputting for y. So keep working to the right. 3 minus 2 is 1. 3 to the first power is 3. 3 minus 1 is 2. So if I plug in 3 for y, I'm getting out, let's say this again, okay? If I plug in 3 for y, oops, notice I need to add this 1 to the other side. That would be a problem, okay? Add 1 to the other side. So it looks like this. So let's go back. If I plug 2 in, 2 minus 2 is 0. 3 to the 0 is 1, and 1 plus 1 is 2. That's better. That's better. If I plug 3 in, 3 minus 2 is 1. 3 to the first power is 3. 3 plus 1 is 4. If I plug 4 in, I'm just going to keep working to the right until I go off a 10 by 10 grid. So 4 minus 2 is 2. 3 squared is 9. 9 and 1 is 10. Well, that's all it's going to fit. I don't need to put another point. It's going to go off the grid. So let's go the other direction from our first input. So here we work to the right of y being 2. Now we're going to make y equal 1. 1 minus 2 is negative 1. 3 to the negative first power is 1/3. 1/3 plus 1, just write it 1 1/3. That's good enough. You can make it 4/3, but why not just call it 1 1/3? Let's do one more just for good measure. But if you have 1, that's good enough. It has a fractional output. 0 minus 2 is negative 2. 3 to the negative second power is 1 over 3 to the second power. That's 1/9. 1/9 plus 1 is 1 and 1/9. Let's plot these points just to see how this graph is evolving. If I go to the right 2, I go up 2. If I go to the right, this is still to the right, and that's up or down. To the right, up or down. So I'm going to the right 4, up 3. I'm going to the right 10, up 4. If I go to the right 1 1/3, just a little bit past this vertical asymptote, it's going to be up at 1. If I go to the right 1 1/9, it's going to be 0. Look how close it is to the vertical asymptote already. But what a lot of students will do is they will connect these points and stop the logarithmic graph. It does not stop. It gets closer and closer and closer to that vertical asymptote, and it continues down forever. Just think, okay? The larger that this y value becomes in the negative direction, the closer this value goes to 0, which means the closer the x value becomes to 1. That's why it does get closer and closer and closer to x equaling 1. It's a vertical asymptote. So now, let's do the range. That would be my next, and I could have filled it in right away. Okay, we really should know that the range, y is the element of all real numbers. Negative infinity to infinity. And you'll see sometimes I put a positive in front of the infinity, but you don't have to. Then the last thing that I would deal with is the x and the y intercepts, because sometimes we stumble upon them right here. Right? If we plug in 0 for y, that's going to give us the x-intercept. I just want you to list it as a coordinate point right here, reaffirming that the x-intercept occurs when the y-coordinate is 0. The y-intercept occurs when the x-coordinate is 0. All we need to do is plug it in here. If this would have been plus 1, we'd have an x-intercept. But if I plug 0 in, the log of a negative number is undefined. We cannot take the logarithm of a negative number. So this is none. Okay? Problem number 10 on this review is going to look like this. And I will say that the piecewise problem that's on the test typically gives students a lot of difficulty. And we have to get better at these piecewise functions. One of the biggest problems is that students forget that they need to plug in 1 into both of these. Even though it's not defined by the second piece, I have to plug it in to know where I'm going to take off. Notice this just says list 6 quality points. I'm not asking for domain and range or any of that. So I can start by plugging 1 into here. But if I recognize that this is a parabola that opens downward before I start, that is going to be very helpful. If I recognize this is a line with a negative slope, that's going to be helpful. I know what my picture should look like. If I plug 1 in and square it, 1 squared is 1. Make it negative. Negative 1 plus 2 is 1 back out. Okay? So if I plug 1 in to that top piece, I'm going to get 1 back out. Now I'm going to work to the left of 1. So if I plug 0 in, I get 2 back out. If I plug negative 1 in, what's going to happen if I plug negative 1 in? Negative 1 squared is still 1. Negative 1 plus 2 is 1. What about negative 2? Negative 2 squared is 4. Make it negative. Negative 4 plus 2 is negative 2. That should give me a good picture of this parabola that's opening downward. If I go to the right 1, I go up 1. If I go left or right 0, I go up 2. If I go back 1, I go up 1. And if I go back 2, I go down 2. That's good enough. I'm not going to fit any more on this 5 by 5 graph that I've provided for you. But now it's going to stop being a parabola that opens downward, and it's going to be this line right here. The biggest mistake is students want to plug in 2 and then have a gap. We don't want to do that. We want to plug 1 in. We don't know, is 1 going to take off right where the parabola left off here? Or when I plug 1 in, is it going to jump up or down and I have to start with an open circle? If I plug 1 in, I get negative 2 plus 3, I get 1 back out. I'm going to circle this. Now I don't want to circle this, but that tells me for the line, I'm going to start right at this point. It's already filled in, so don't circle it. And now I can just count the slope from that point, which is down 2 over 1. Down 2 over 1. Down 2 over 1. Down 2 over 1. And the only difference is that it takes off at this angle like this. Okay? There it is. Questions on that one? Okay? Obviously, it's recording. Problem number 11. For problem number 11, this is on composites. Remember, a circle means composite, not multiplication. So we want to find f of g and g of f. And then we want to give the domain of f and g of f. List all domains in set builder notation and interval notation. So start out. We're just going to find the domain of these two. Okay? The domain of f. The domain of f is going to be in set builder, x is the element of all real numbers, such that, remember I'm setting this greater than 0 and subtracting. X is greater than negative 2. How do I write that interval notation? Parentheses, negative 2, infinity. Remember, you're going to have your choice. You will have your choice after chapter 1. I got to be careful here. It's x is greater than or equal to, right? X plus 2 is greater than or equal to 0. We can take the square root of 0. Okay? So I have an equal to here, which means we have a bracket here. So be careful about that. You will have your choice after chapter 1 which one you want to use, set builder or interval. The domain of g, well, this is just a parabola. X squared minus 2, that's a parabola that opens downward. We can plug any value in. The domain, x is the element of all real numbers. Written in interval notation is negative infinity to positive infinity. Okay? So now let's find the composites. F of g of x. I'll show the work right here. F of g of x. Remember, x goes into the g function. Whatever comes into the g function, x squared minus 2 comes out. Just a machine. Now, we're plugging this is the input, into the f machine. X squared minus 2 comes into the f machine. The f machine says whatever comes in, add 2, and then take the square root. I can cancel the 2's. Never cancel terms and factors in the same step. And then I show that the square root of x squared is x. Some people want to make this plus or minus x. That is not true. If we wanted plus or minus square root, we would put it right here. This is the principal square root. It is the positive square root. It's not plus or minus. Our composite is x. What is the domain of this composite? The domain of this composite looks like it's all real numbers. But be careful on composites. You always have to check the domain of the interior function to see if it's more restrictive. The domain of g of x was all real numbers, so we're good. The domain of f of g is all real numbers. There it is in set builder. Here it is in interval. Let's do the composite the other way. So looking, I still have those functions up there at the top. I'm going to write it right here, g of f of x. And I want to see some processing here. Take x, plug it into the f function. This comes out, x plus 2. That's the output from the f machine. But now the output from the f machine is going to go into the g machine. And the g machine, looking right here, says whatever comes in, square it and subtract 2. This is coming in. We're going to square it and subtract 2. If I square a square root, it gets rid of the square root. And when I subtract 2, look what happens. We get x again. We get x. So the composite here is x. And again, it's not plus or minus. Here's the tricky part. This is going to happen on the test. One of the domains for the composites, I'll tell you right now, is going to be restricted. You have to be able to identify which one it is. The domain looks like it's just all real numbers, but we have to check the domain of the interior function, f of x. Did f of x have a more restrictive domain? Yes. The domain of f was x had to be greater than or equal to negative 2. So our composite has to take on that more restrictive domain. You only have to check the interior most function. So the domain here is x is the element of all real numbers such that x is greater than or equal to negative 2. Bracket negative 2 to positive infinity. Remember, it's the interior function. If it has a more restrictive domain, then your composite must take on that same restriction. One of the two is going to be restricted on your test. It is on the take-home test too, so you should be able to get used to it if you're following this video. Okay? The fact that we had x out of both of these tells us this. We could actually make this statement, since f of g of x equals g of f of x equals x, the functions are inverses. Now, it didn't ask you to verify that they're inverses on this problem, so it's not necessary, but it's going to come up on another problem. Then we go to a little bit of trig, where we're changing from degrees to radians. Leave the answer in terms of pi in both these, so do not give a decimal answer. It'll be a non-calculator question. 60 degrees, I would expect that you can recognize that as pi over 3. And 1 will be a recognizable, okay? If this was 120 degrees, it'd be two 60-degree angles. It'd be 2 pi over 3. If this was 210 degrees, that's 7 30-degree angles, 7 pi over 6. I want you to be able to convert them that quickly. Negative 135 degrees. Well, that's 3 times 45. 45 degrees is pi over 4. I need 3 45-degree angles. I need to put a negative in front of it. Negative 3 pi over 4. That's what I'm looking for, is easy conversions. Likewise, going this direction. Pi over 3 is 60 degrees. 60 times 5 is 300. I have to put the negative in front of it, and don't forget your degree symbol whenever it's a degree. If there's no degree symbol, it's assumed to be radians. Pi over 4 we know is 45 degrees. 45 times 5 is 225 degrees. I would prefer that you not have to write anything down to do the conversions, and it would be like that on the test as well. Looking at problem number 14. This is really one of the reasons why I'm processing this and not just talking through the solutions. We have to be able to identify these 5. I wish I would have ordered them a little bit differently, so it may be a different order on the take-home test and the actual test, but it really shouldn't matter. First of all, the center line, remember, is the number that's by itself. It's a separate term. It could be in the front like it is here, or it could have been a plus 3 in the back. but a center line is always y equals the y, or that number, okay? Period. The standard period for sine and cosine is 2 pi. So to find the period, I have to take 2 pi divided by this coefficient right here. Sometimes it could be inside the parentheses. But if I distributed this, it would be 2 times x. It is the coefficient of x, so I call that c. So the period is going to be 2 pi over whatever that coefficient is. That coefficient is the number outside the parentheses or the coefficient of x, depending on how the original problem is presented. So this is 2 pi over 2, which is pi. That's period. Remembering that the increment is always just a fourth of the period. It's pi over 4. Amplitude. This one, a lot of students miss because remember this is a negative sign here, but when we list the amplitude, it's always the coefficient of the sine or cosine function, and it's a positive number because it's the distance away from the center line, either up or down, the maximum distance away. The phase shift is whatever is being done to x, but it's the opposite, right? So it's really, the phase shift is whatever makes the argument equal 0. It's the most interesting value of x. It's pi over 3. The phase shift, I like to remember, is the starting point, okay? So here's what we do then when we graph this particular function. The very first thing we're going to do using this information is we're going to draw our center line. We are not going to draw in the y-axis. That will create problems for you on the test and the take-home test if you do that. And then we just have to be really good at adding fractions. That's all we're doing. But we're starting at the phase shift. It's a positive phase shift, so I'm going to put it about here, because I have to work backwards until I hit 0 or a negative number to know where my y-axis is, okay? And remember, I'm just adding my increment or subtracting my increment. So I'm going to write real quick on the side here. The lowest common denominator here is going to be 12. So really, I want to think of my phase shift as being 4 pi over 12 multiplied by 4 over 4. And my increment multiplied by 3 over 3 is 3 pi over 12. So if I have 4 pi over 12 and I subtract 3 pi over 12, I have a positive pi over 12. I still need to go backwards at least one more. Pi over 12 subtract 3 pi over 12 is negative 2 pi over 12, or negative pi over 6. You have to reduce the fractions. Okay? But now that I hit a negative number, I'm good. I don't need to keep working to the left. I might as well work to the right. Remember, this was 4 pi over 12. I'm adding 3 pi over 12, so that's 7 pi over 12. 7 pi over 12 plus another 3 pi over 12 is 10 pi over 12. 10 over 12 reduces to be 5 pi over 6. I could keep going here, and I'm going to do this just so you get used to the fractional part. 10 pi over 12 plus 3 pi over 12 is 13 pi over 12. 13 pi over 12 plus another 3 pi over 12 is 16 pi over 12, which reduces to be 4 pi over 3. 16 pi over 12 plus another 3 pi over 12 is 19 pi over 12. And I could keep going. As long as you give one period, that's good. Remember, this is my starting point, so a lot of times I will lightly circle that as soon as I put it on my center line, because this is where I have to start this curve. Remember, the starting is the key. Once you get it started, it's fine. Remember that sine starts on the center line. It would go up first if we have a positive amplitude coefficient. It would go down first if we have a negative amplitude coefficient. But this is a cosine function. Cosine starts off the center line at the phase shift. If we have a positive amplitude coefficient, we would start up here, just like the normal cosine does. But since we have a negative amplitude coefficient, we start down here. So you have to know the 4 ways that you start. 2 for sine, 2 for cosine. Because once I have a low spot, I know I have to cross to hit a high spot. I have to cross to hit a low spot. I have to cross. I need to work backwards here. I need to cross to hit a high spot. And then I just sketch this in, trying to make sure that this distance is about the same. I'm not going to get out a ruler, nor do you need to. We need to make sure it's about the same. And then we sketch it in. Remember, this part here is called concave down, and we'll talk about that in a later chapter. And up here is concave up. It's changing from that bowl shape down to bowl shape up at the center lines, always. And I could have kept going, but I want to have a spot where I can put the y-axis in where it belongs, which is going to be right in here. Now I made it a little bit closer to pi over 12 than to negative pi over 6, because this is closer to the y-axis, but it really doesn't matter, as long as it's in between the negative and the positive. And the last thing we do is label the center line and add and subtract the amplitude. So we're going up to 5, we're going down to 1. Okay? There have been times when I've asked about the domain and range of this function. The domain is all real numbers. We can plug anything into a sine and cosine function. But the range would be y is greater than or equal to 1, less than or equal to 5. So bracket 1, comma, 5, bracket. That is the graph of the sinusoid, and it's very much like the one that's going to be on the test. You can get 5 of the 8 points if you know how to identify these. This is probably the most important. The second is being able to add these fractions along the bottom. Okay, one of the more detailed problems is going to be this one, finding the inverse of this rational situation, and then verifying the composites. Write a summary statement that verifies your proof. You have to have this, and I'll write it on here so that you can see it. We work these the same way that we always have. Write it using x and y. Switch x and y. And now we have to resolve for y. For some students, doing this process can create some difficulty. But remember, I always say, hey, what choice do we have? If we're solving for y, we have to get them all on the same level. I can't have some in the numerator, some in the denominator. So I have to multiply both sides of this equation by y minus 2. It's the same thing as cross-multiplying the denominator up, right? The denominator here is just 1. So now, what's causing the problem? These parentheses. I have this y inside there. Okay. So I guess to eliminate parentheses, we know we distribute when we have a factor outside parentheses. Now, I want to solve for y. Well, there's 4 terms. 1, 2, 3, 4. 2 of the terms have a y. 2 do not. Get the 2 terms that have y on the same side by subtracting the y over here and adding the 2x to the other side. And then how do I make 2 terms involving that variable become 1 variable on that side? Well, you factor it out. It's called the greatest common factor. And now if I want to get y by itself, I divide both sides by the binomial of x minus 1. There it is. We should write it using inverse notation. So we keep the 2 functions straight. I'll write it down here. There is our inverse function. Before you check the composite on this problem, I want you to make sure that the asymptotes have switched responsibilities. So let's take a look at this. In the original problem, we had a vertical asymptote of x equals 2. That means the horizontal asymptote should be y equals 2 here. It is. In the original problem, we had a horizontal asymptote of y equals 1. That means the vertical asymptote here should be x equals 1. We're pretty sure that this is the inverse. But now I have to crank out these composites. So I've given you a whole page to do this. we have to crank out these composites. I'm going to write the inverse function up here as well, so I can reference them right next to each other. Notice here the domain of this inverse is that x cannot be 1, which makes sense. That was the horizontal asymptote here, so of course, that's the vertical asymptote here. So it's eliminated from that. So let's do the first one. F of f negative 1 of x. Take x, plug it into the inverse function. This comes out 2x plus 1 over x minus 1 comes out. And now that's going into the f machine. Sometimes it's good to just use, that is going in here and here into the f machine. That x and this x. So we end up with 2x plus 1 over x minus 1 plus 1 all over, comes in here, 2x plus 1 over x minus 1 minus 2. I would like you to see you be able to go from complex to non-complex in one step. I am simply multiplying 1, 2, 3, 4, all 4 terms by the denominator of x minus 1. That's the same thing as multiplying this big fraction by x minus 1 over x minus 1, which is algebraically legal. If I multiply this fraction by x minus 1, it cancels, and I get a 2x plus 1. I have to multiply this by x minus 1. 1 times x minus 1 is just x minus 1. Have to do the same thing down here. If I multiply this by x minus 1, it cancels, and I'm left with a 2x plus 1. If I multiply this by x minus 1, I get negative 2 times x minus 1. Now, if you skipped that step and went straight to this step, I'm okay with that. I just want you to make sure that you are careful and that you distribute that negative sign to both terms, because that can be problematic if you forget to do that. Negative 2 times negative 1 is positive 2. But this is critical, and points will be taken off if you try to cancel terms and factors in the same step. Okay? I forgot my plus sign here. So it's a little confusing. So I cancel these first. Then 2x plus x is 3x. In the denominator, I'm going to cancel the negative 2x and the positive 2x. 1 plus 2 is 3. Then I show the cancellation of the factors, and that's how I'm processing this out correctly to be x. We know the answer is going to be x on these. But trust me, if you fake it, I'm going to be able to tell. So make sure that you're processing it correctly. Now, let's process it the other direction. Here it is. F negative 1 of f of x. Take x, plug it into the f function. This comes out. X plus 1 over x minus 2 comes out. And now that is going into my inverse. And you have to be clear about which direction this goes. Be detailed in your work. This is going into my inverse function both here and here. Here it is. I'm going to write it here so we can see it. Okay? It's 2 times this input. Here's the input, x plus 1 over x minus 2. Okay? Plus 1. All over the input minus 1. Here's the input, x plus 1 over x minus 2 minus 1. There it is. You just have to keep track of where it's going into. It's going into my inverse here and here. Actually, I probably could have seen it right here. Right here and here. To go from complex to non-complex, I would not distribute the 2 first. Just multiply everything by x minus 2. If I multiply this term by x minus 2, it cancels, and I'm left with 2 times x plus 1. Don't forget your parentheses. But I have to multiply that by x minus 2. If I multiply this fraction by x minus 2, the numerator cancels with the denominator. I just have x plus 1. If I multiply this by x minus 2, I get negative 1 times x minus 2. So now if we distribute the 2, we get a 2x plus 2 plus x minus 2 over x plus 1 minus x plus 2. These terms cancel. 2x plus x is a 3x. These terms cancel. 1 plus 2 is 3. Never cancel terms and factors in the same step. But now I can cancel the 3 and we get x. It works. We got x out both ways. I have to write this summary statement. Again, we're practicing being concise with our verifications. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. A couple things as we're writing that I have not pointed out as much as I should have in class. Notice I didn't say they are inverses. No pronouns, ever. We never want to use pronouns, particularly they and it. Do not use those, okay? Just say the functions are inverses. If this part, remember this part should not be confusing because I give it to you right here. You're just restating that, okay? There's that problem. Okay, I'm going to send this out as review solution video part 1. It'll come out in 2 pieces because it's going to take some time to work through this. Obviously, it's already been an hour. And then I'll send the other one out as part 2 when we start with problem number 16. That's why this used to be a 2-day test, but remember, this will be cut down for in class so you can get it all done in 1 day. But we're going to do the second part then as a separate video. Okay?